Good morning, everyone. We're back. I'm Dave, for anyone who didn't come yesterday. I heard the drinks last night went until about 9 a.m. Anyone stick around for those? 9 a.m., 9 p.m. Oh, geez, you can tell how much of a late night it was for me. Yeah, thanks for all the great energy yesterday. I hope you guys enjoyed all of yesterday's talks and the talks at the end, the little science comedy thing that we had for you, as well as all the drinks and food. Yeah, did everyone stick around for that? Who stuck around? Can everyone raise their hands? Was anyone there? Great, love it. Leave your hands up if you had a good time. All the hands went down. Nah, just joking. Cool. Well, I hope you guys had fun. And we've got another day of talks for you guys today. I'm really looking forward to what we have all throughout the day. But in the meantime, let's introduce back Tim for reflections from yesterday and agenda setting for today.
Thanks very much, Dave. Thanks everybody for getting here at 9. So yeah, look, I just wanted to thank everyone for yesterday, particularly the comedy. The comedy was great. It was Min's suggestion that we should try this out, and I think it was fantastic. So thank you for everybody that was involved and for everyone who enjoyed the evening. I had a really good day yesterday. The talks were amazing. The feedback we constantly get whenever we do these things, and I got a lot of yesterday, was it's just great to see the diversity of work that's being done within AuScope. People don't realise how broad the sort of discipline area is and how broad our reach is within geosciences. So thank you for everybody who engaged in that and gave us good feedback. Speaking of feedback, you might not have noticed, but there are some QR codes on our little badges. We forgot to mention them yesterday. If you take a photo of the one on the front, you'll get sent to that person's LinkedIn page. But if you take a photo of the ones on the back, you can see the program, and the bottom one is for you to give us feedback on the conference. So please, when you have a chance, give us some feedback and let us know what we did right and what we did wrong and what we could do better next time. While I'm talking about merch, don't forget, particularly those of you who run labs and have facilities, please grab some of these and stick them around your facilities so we can get some QR code linking through to how to reference AuScope in publications and things, but also just to get some branding on the facilities. And there are the other little round stickers as well. I just wanted to also briefly touch on the outcomes from the Slido exercise we did after our little breakout groups. So we offered you $10 million, asked what we should do, and the responses were fantastic. And they sort of fell into a few groups, and very pleasing groups. I think the first thing was that everybody said you found someone you could collaborate with. So as I said, that was one of our intentions. Very pleased to see that you were able to identify a way to collaborate within your little groups. About half the responses talked about outreach, outreach to secondary school students, outreach to primary school students, outreach into traditional owner communities. And it was fantastic to see that focus and fantastic to see the work that SEMA and others are doing in that space is cutting through. But, you know, obviously there's a lot more that we need to do to address those issues that were raised yesterday. There were lots of submissions that talked about sort of multi-physics and data transects and multi-observational transects, which is interesting because the original AuScope model had these geotransects as one of its core components, and we did that for a long time. And I guess we've moved away from it a little bit recently, so maybe it's something that people are suggesting we should look at again. We'll definitely do that. And then the other one was really around data discoverability and interaction with data and portals and visualization of data. So obviously something that falls within Beck's portfolio and something that we are certainly aware of and addressing, and is a common theme in the responses we get. So whilst we don't have $10 million to throw at you just yet, we'll certainly build that into what we do going forwards. So that's all I wanted to do. I'll hand back to Dave because I think he's going to introduce our keynotes this morning.
Thank you so much, Tim. So we've got back for you guys, special treat. We have Professor Graham Heinson, who is a globally recognized leader in geophysics, whose pioneering work has transformed, I'm going to not say this word correctly, magnetometry autotellurgic methods from academic tools into powerful instruments for exploring mineral, energy and water resources. Since joining the University of Adelaide in 2000, he has led major innovations in geophysical research and infrastructure, including the development of national MT capabilities and the landmark AusLAMP project. His collaborations with industry and government have advanced resource discovery, environmental monitoring, and hydrogen exploration. Thank you so much, Graham. Would you like the mic or would you like these bad boys? Here we go. Thank you so much. Let's give him a round of applause.
Hey, thank you very much, Dave, and thanks, Tim, as well. So the last part of that was hydrogen, which is what I'm going to talk a little bit about today. So going back almost 40 years, 1987, drilling program in the Western African country of Mali discovered not large flows of water, which is what they were drilling for, but large flows of hydrogen, natural hydrogen. Had 98% purity, 1% methane, and 1% nitrogen. So that was a sort of unexpected and unpredicted result, drilling through sedimentary layers into Precambrian basement. Subsequent to that, a company called Hydrotherma drilled another 24 holes, some of them quite shallow, only a few hundred meters, and discovered significant amounts of hydrogen at depths of 100 meters, capped by carbonates within these sedimentary sequences. And since 2012, a power plant has been running on that natural hydrogen. It's about 50,000 cubic feet of hydrogen produced per day, and that powers one village of about 1,500 people in Mali. So it was the world's first, but only, hydrogen power plant in the world. So the question is this a unicorn event? Is this one-off? Or is hydrogen available and around everywhere in commercializable and energy production quantities? And there's been a very significant amount of investment and interest in that paradigm ever since. So part of the problem is understanding how hydrogen is generated in the Earth and how it's migrated and how it's trapped. And there's three primary mechanisms that have been postulated. There's actually quite a few more, but the main ones are serpentinization of mafic rock. So that's the water interaction with iron-rich rock. There's radiogenic elements of uranium and thorium that interact with groundwater and produce both hydrogen and helium. And there's potentially mantle degassing of hydrogen and potentially helium, helium-3, in certain locations of large lithospheric faults. Now, natural hydrogen has been a very attractive energy source, so it's estimated that it will cost about $1 per kilogram of hydrogen to produce energy, and that's significantly less than any other mechanism of producing hydrogen through renewables or fossil fuels. It's also carbon-free, and as a byproduct, helium-3 in particular has a value of somewhere between $20 and $28 million per kilogram, because it has very specific uses in quantum computing and potentially nuclear fusion. So it's extremely rare, extremely valuable. So the slide here shows some of the geological potential paradigms which may produce hydrogen. And I'm not going to go through them today, but just to say, we still really understand very little about how hydrogen is generated within the Earth and where it may occur. So much of the exploration strategy for hydrogen really has been a top-down process of looking at soil samples, maybe sampling groundwater, and really trying to identify where hydrogen comes out of the Earth and locate hotspots. And there's been very little science sort of underpinning the the bigger question about where is it generated, how is it migrated, and how is it trapped? And so to address some of these questions, we were invited as part of this Cooperative Research Centre project, CRC-P, which was led by an industry group in West Australia called H2EX. And just to give a background on CRC-P projects is that they are sort of mini CRCs. They're a perhaps 2 to 3 year industry-led program that has not necessarily straight commercial outcomes, but leads to that path of commercialization. But it's also designed to provide primary science to these questions and problems. So H2EX partnered with Australian National University, University of Adelaide, CSIRO as the research partners, and with service contractors, Fleet Space Technology, and Black & Veatch. And the idea was we would look at an area, understand its fundamental physics, understand its fundamental science and chemistry, and try and have a strategy to locate hydrogen from a very scientific viewpoint. So AuScope play a big role in this, and the reason I'm talking today was to talk a little bit about how the various nodes of AuScope came together to make this possible. So the largest component was Earth imaging. So this is primarily the seismic ambient noise tomography and seismic imaging that the ANU group did, the MT imaging that my group at the University of Adelaide do, providing the software tools developed at both of those universities, providing data from the AusPass catalogue and from the NCI for the magnetotelluric catalogue. And very importantly as well is in the training of students. So we have 4 PhD students training in this area of a very rapidly developing industrial sector. So Earth imaging was a big part. We used the catalogues of Australian seismology or seismometers in schools as part of that earthquake catalogue. And also finally, simulation and analysis and modeling with Louis Moraesi's Underworld 3 to really quantify the geodynamic setting. So where were we? Well, we were out in the field. There's a few pictures of the teams in the field. There were 3 main phases of field work. A pilot study to sort of assess the potential and the feasibility. A much larger sort of regional study of about 150 instruments spread over a grid. And then a very detailed surveys to identify trapping mechanisms. So the area we were looking at was the eastern side of the Eyre Peninsula, so it's part of the Gawler Craton, and it really lies on a belt of remarkable geology. It's the sort of Proterozoic Olympic Dam domain. It's Proterozoic basement. It has high radiogenic element concentrations. There are areas of Neoproterozoic and subsequent other sedimentary cover. It's a big focus of hydrogen exploration led by the South Australian government. There is an active lease on the Yorke Peninsula with Gold Hydrogen, who discovered a very significant flow of hydrogen and helium at their Ramsay well in the southern part of Yorke Peninsula. And the area we were looking at was the Eyre Peninsula on the eastern side, around the towns of Cleve and Cowell. Now, these are interesting because they are Proterozoic rocks. They have Paleozoic sediments over the top in places. They're an area of significant earthquake activity. I've sort of highlighted the area, but I'll show a few other slides a bit later of what we were looking at. It's reasonably well characterized by geophysical information, and we have background regional sets of both passive seismics and MT. So we actually knew the regional setting of the structures we were looking at. But in a nutshell, there is a very significant fault running around the eastern side of the Eyre Peninsula called the Kalinjala Shear Zone. And then there's subsequent, possibly similar lithospheric scale faults and they're splays of a fault called the Shoal Point Fault, in particular in the Jungle Dam Fault. And these act as big structural boundaries that potentially there also are flow paths for hydrogen. So what do we do? Well, I mentioned we did MT. So we use the Earth imaging capability of the AuScope. And really, there is nothing comparable in industry that could be have deployed in this manner. So we put out 150 MT sites. You might just be able to make them out as these black triangles on the map. And we also did much finer, much higher resolution MT surveys on these blue transects. Their sites were about 500 meters apart, whereas the bigger regional survey was 5 kilometers apart. What I plotted on the top of there are the yellow and the green dots are earthquake locations from the AusPass catalog and also from Geoscience Australia. And then the colored image beneath it is the electrical resistivity at 5 kilometers depth. So the reds are very conducting and the blues are very resistive. And just for a little bit of context, the bigger fault on the right-hand side, so the white dashed lines are the faults. The one running up on the furthest on the right-hand side at the bottom, that is the Kalinjala shear zone. So it's a big lithospheric fault. We know that this runs deep and it separates significant changes in geology from the east to the west. So from the MT data, we ran three-dimensional inversions, we created a three-dimensional model, we sliced it, and what I've done here is just shown two slices through the 3D model. So on the top figure on the right-hand side, the yellow lines just show the transects we've taken, a sort of radial arc from the northeast or northwest corner, and sliced the Earth down to 25 kilometers. And you can see those two cross sections at a 20-degree angle and 30 degrees. We chose those partly because those are the angles we estimate from the Australian stress map as being the direction of principal stress in this environment. So the red shows the conductors, and there is an enormously conducting signature in the middle of these profiles. The blues are resistive, and they tend to be regions that have been removed any kind of volatiles, anything that will conduct electricity. So on the right-hand side, the blue region is what we call the Donington Suite. It's a granitic region, potentially full of radiogenic materials, but it's from a melting of the lower crust. So it is sort of denuded of anything that will conduct electricity. The big red sort of bowl of conduction is, we think, graphite. And we think that because graphite occurs at the surface. So in some places, the graphite is extruded and risen to the surface and it is commercially mined. And what we've done with this map is to draw in, based on the resistivity, primary faults and structures. We know where they occur on the surface. We infer their dip. And from the AusPass catalog, we plotted earthquake locations with depth and lat long, and we can more or less map out the depth extent of these faults. So that's important for the hydrogen paradigm in that it maps potential migration paths. These are highly seismically active faults with magnitudes up to 5 to 6. So we generated a 3D model, we filled in the detail, and we can map quite well the geology from the surface down to about 20 to 30 kilometers. The passive seismic array followed the MT array. Well, it was done simultaneously. Passive seismics as a larger array was left out for just over a month, I believe, and had the same aperture and more or less the same site locations as the MT. It was followed up by a number of smaller transects of higher detail to define more detail in the top 1 to 2 kilometers. And from the ANT, so ambient noise tomography, we can cut the same structures out in the 3D model. So the blues are slightly higher, faster velocities, the reds are slightly lower velocities. What we're mapping here is the sedimentary cover over the surface, the change in the rheology and the structure of the Earth at various levels, and we plotted the faults as we had from the MT on those maps to indicate essentially how that similarly blocks and divides the Earth up into discrete regions. From the seismic array as well, we can use the horizontal to vertical spectral ratios to give us an estimate of the depth of sedimentary cover. So the blues here show the deeper thickening of sediments, and the reds show shallowing. And these are the sites on the edge of the, there's two basins on top of each other, the Itildoo Basin and the Polder Trough. And we map really quite well the sedimentary thickness over Precambrian basement here. And this is an important potential trapping mechanism for hydrogen of having sedimentary strata underneath radiogenic or mafic basement. So once we'd had some idea of how the faults were located spatially in 3 dimensions, we had an idea of the dip and the lateral and vertical extent. Louis Moresi modified Underworld to develop it as a tool for understanding the potential flow paths of hydrogen from mid-crustal depths. And we're estimating if we have serpentinization, typically the peak serpentinization rate of hydrogen production occurs at about 350 degrees centigrade, about 15 kilometers into the Earth. Radiogenic production of hydrogen may occur at all depths, but we're taking a deeper source of hydrogen, funneling through these faults, and predicting where they would occur based on the regional stress field and the orientation of these faults. So this relied on the Earth imaging models, seismic and MT combined together, to provide the framework for the geodynamic sequence. So the first part was to construct a 3-dimensional geological model in Underworld. And then Louis then calculated the strain based on the regional stress field. And the red line, basically, this is a sort of plan view, the top of the model. The red line indicates maximum strain, and that maps out the Kalinjala shear zone in that southern part of the Eyre Peninsula. As you move north in the Eyre Peninsula, there is a whole succession of the splays of the fault, and they seem to distribute the strain more generally across a number of faults rather than a singular one. But in particular, what we were looking at was where some of the faults joined together to produce perhaps zones of higher permeability and greater flux of hydrogen. So based on those models, we could predict the strain rate and then the surface flux of hydrogen coming up from depth. And therefore, we've got a predictive system to predict hydrogen at the surface. And therefore, that's a much more scientific approach to hydrogen exploration, is understanding where we might find it before we go off and perhaps look at soil samples, groundwater samples. So from all of the geophysics and all of the geology and all of the geodynamic modeling put together, we came up with a scenario for the geological provenance of this region. And the scenario is essentially that we've got a big basin of carbon-rich sediments deposited at the end of the Archean before the Great Oxidation event. We've got compression through a series of orogenic events, thickening of those sediments, and in particular, melting of the crust during the Cornean origin. That produces the Donington Sweep, which has large amounts of radiogenic elements, a squashing and thickening of that sedimentary pile in the middle. And if you take carbon-rich sediments and you heat them up to about 500 degrees centigrade, the carbon turns to graphite, and the graphite is our conductor. And then subsequently, there's been transpressional movements from the Kimban origin, further orogenic events, but largely it's undisturbed since the Mesoproterozoic. So we developed this geological model as a method of then defining, I'll just move to that one, of defining where we might see hydrogen as a source. So the Kalinjala shear zone, which is the larger fault running on the right-hand side of this diagram that intersects the mantle. This is well known as a big lithospheric scale fault, a potential pathway for mantle hydrogen. Within the crusts of the lower crust, we may get mafic serpentinization, and that's from meteoric water through the major faults, such as the Kalinjala, and the generation of hydrogen from serpentinization. And then I've also shown in the middle of the sedimentary pile, we have small amounts of volcanics. This is the Peter Pan suite, which are radiogenic, and those occur in small areas, and they also may be a source of radiogenic hydrogen. So we tried to define a geological framework from which to find hydrogen, and then we've been looking more recently at more surface formations to understand something of the trapping mechanism. So we worked closely with H2EX. It was a fantastic project, very collaborative, regular meetings, a real hands-on approach to understanding a problem from a junior company that really wanted to understand the problem, understand the questions involved in hydrogen exploration. It's a big boom industry at the moment. There's a lot of investment going into it, and we need to see that we have a good scientific approach to understanding how we might turn small amounts of hydrogen we see on the surface and understand how that may relate to bigger commercial quantities of hydrogen in the crust. So Mark sent me a few comments. They were very pleased with the collaboration, very pleased with the output, and they are currently planning a drilling program based on these results. So just as a conclusion then, this really demonstrated the value of AuScope collaboration. We provided equipment, people, expertise, data, software that really is not available commercially and not available through the scientific expertise of the group involved. We trained a number of PhD students in this rapidly evolving industry, and I'm sure they'll have a great future. And we hope that we will find hydrogen, or they will find hydrogen, and it will promote further research into the hydrogen industry globally. And their success is our success. And we hope in about a year's time, we'll be able to be here, if we're here for another AuScope meeting or similar, that we can talk about what results have come out from this drilling program and other drilling programs in the area, and to see how this hydrogen industry develops over the next few years. So with that, I think we'll finish. Thank you very much.
So much. Let's maybe do like 5 minutes of questions. So we'll do about 5 minutes of questions. Oh, we've got one already at the back.
Thanks very much, Graham. Fascinating project. What's the relationship between the fault structures you've identified as possible pathways and the discovery well?
So at the moment, there are no drill holes for hydrogen on the Eyre Peninsula. So the major hole which has been drilled in the area is on the York Peninsula, so that's the Ramsay 1 well. So that well mirrored a well which was drilled in the 1930s for oil that produced a lot of hydrogen. And Gold Hydrogen are drilling new targets in the next few months. So they're targeting essentially the Stansbury Basin sediments over the Proterozoic basement. So probably just one point I probably should have made is that, of course, the scenario that is in Mali is also in Australia. So there are a lot of analogues from the geological framework of that discovery in Mali that we see here in Australia generally, but certainly in the Proterozoic part of Australia. So this gives us great hope that when the drill holes do happen in Eyre Peninsula, that they will be similarly successful.
Is there another question? Oh, down here, Tim.
Thanks, Graham. Fascinating talk. Are the types of traps that you would trap hydrogen in the same as the sort of traps you would trap hydrocarbons in?
That's a very good question. And you know, hydrogen is obviously much more mobile than hydrocarbons in gas or oil form. And as such, I think the common wisdom is we don't have permanent traps, but we have baffles. So baffle is basically a slowing of the movement of hydrogen and therefore accumulation of hydrogen underneath them. In terms of the trapping mechanisms in Mali and also probably in York Peninsula, it's carbonates. I think there's a lot of research that could be done understanding potentially how hydrogen moves in the last few hundred meters through these sedimentary sequences. We probably understand that there is hydrogen coming out from the crust because the reactions are well known, but the actual migration is much less well known. And I think there's a lot of scope to discover more there.
Do we have one final question in the middle? This will be our last question.
Thanks. Fantastic talk. Really interesting stuff. But you mentioned helium and the value of helium up front. Why is it not a helium industry?
That's a very good question. I think this has sort of become as a byproduct that some of the companies realize may be a more valuable asset than the hydrogen asset. So there's one producing helium-3 mine in the world, in the United States. But it obviously is an incredibly rare commodity. And if helium-3 can be harvested in any production scale, then it is worth a lot of money to these companies. I guess they pitch themselves as hydrogen, so that's where they're going. And, you know, down the track, and of course it is the carbon-free or low-carbon energy source that may be transformative. I suspect no one's thinking of it as a sort of national grid scale, but in terms of powering industry or mines or particular smelters, for example, it may be a fantastic source where locally produced hydrogen produces energy almost on site to a local industry. So the hydrogen story is probably the long term, but the helium may also generate a lot of money for some of the explorers.
Well, thank you so much, Graham. Let's give a round of applause.
Question.
Oh, all right. So, oh no, I left my... Not doing a very good job sometimes, Dave. Here we go. Need my bio. Also, very big fan of the black and black and black. Not that we coordinated, in case anyone's wondering. So we have Dr. Sarah Kachovich. I feel like I should get it right. Sarah's been, we know each other, is a radio laureate micropaleontologist and the ANZIC program manager for the Australian and New Zealand International Scientific Drilling Consortium. She's based at the Australian National University and for the past 9 years has been deeply immersed in every facet of scientific ocean drilling, sailing as a shipboard scientist, technician, and science communicator on 6 IODP expeditions aboard the geodesy Resolution on each of the 5 oceans. For the past 4 years, she's been helping steer ANZIC's strategic direction through the program's most turbulent decade, including the pandemic pivot, the 2024 retirement of the JR, the end of the IODP program, and Australia joining the ICDP. Ladies and gentlemen, please give a round of applause for Sarah.
Thank you. I'll just click through. Fantastic. So today I'm going to tell you how we collect these cores and what these cores mean for Australia's resilience. So ANZIC, in a nutshell, on one line, ANZIC equips scientists in Australia and New Zealand with the skills, global connections, samples, and data needed to explore Earth's dynamic processes, future and past. So our vision is ANZIC-led deep Earth discovery, probably not as deep as many people here, and might argue otherwise, but it is deep Earth discovery. It drives a resilient and sustainable society. We have 4 strategic pillars in ANZIC. It's to nurture partnerships, facilitate access to infrastructure, and foster the skills pipeline. And lastly is the demonstrate outcomes and impacts. So this is something we're doing a little bit more, that last point. So I think a few people have seen ANZIC talks before, or IODP, ICDP talks before. Hopefully I'll give you something a little bit different today, that kind of end pathway, those impacts. So ANZIC doesn't give, we don't own drill ships or infrastructure, so to say. We're a little bit different to AuScope. We give access to that infrastructure, and ideally these 2 international research collaborations dedicated to advancing scientific understanding of Earth through drilling, coring, and monitoring the subsurface. So you can see down the bottom, there's ICDP, that's the current one, the Continental Drilling Program, and the current ocean drilling program is IODP 3. So we have this big sleuth of acronyms for the ocean drilling program. I won't go into too much detail, but I will say ODP a few times, so that's the Ocean Drilling Program, and much older is the DSDP program, which I will also mention, so that was the first one. And both programs collect sediments, rocks, fluid, and microbes, and data. So scientific drilling is a critical tool to explore deep time. I like to think of the program as a time machine and probably our best chance of actually going through time. It's a critical tool to probe the interconnected Earth. So we study life, climate and environment, dynamic Earth. That's the ocean program. And for the continental program, very similar, but a little bit more focused on the resources like geothermal as well. And it's a critical tool to address fundamental questions about Earth and its responses, and that's responses to climate change, to geohazards like volcanic eruptions, earthquakes, and so forth. So the drilling infrastructure capability, we've compiled this little graphic here to quickly capture, so going from left to right. So the ICDP program do a lot of floating barges, so they can go down quite deep. Recently, they've just drilled the Tibetan Plateau and one of the lakes up there. There's been a lot of lake drilling recently too. So we also do hard rock drilling in the ICDP program, so that can go much deeper down. The lift boat, this was famously used for the Chicxulub crater expedition to see how the dinosaurs died. More recently, there's been hiring of academic fleet, especially with the retirement of the JR. So famously, let me see if the laser pointer works. This here, just like the prod. So Jodie Webster used this recently offshore Hawaii. So we don't have to drill from the vessels, we can drill from the sea floor. This will be a great investment, I think, for Australia if we get our own seafloor drilling and we can put it on the Investigator. A little bit of this guy's here, mostly to collect the data from the corks here. which are deep hole observatories. So we instrument a lot of boreholes. We've done about 30 across the oceans for the ODP and IODP. We can also drill from industrial geotechnical vessels, but we go a lot shallower. More famously, for most of the IODP history, we've done the deep sea drilling through drilling vessels, the JR, Chikyu, and there's a new Chinese vessel. So that can go down about 7 kilometers, a little bit more for the riser drilling. And I just wanted to highlight the Space 2C program. So infrastructure can be built in hometowns. So the New Zealanders have actually built this hot water drill and coring facility. And so they go through the ice shelf, and they're actually attempting again for the 3rd time this season to go down 200 meters right at that grounding line into Antarctica to understand if the climate, the Paris agreements to, actually, sorry, I'll move on. I don't have much time. And there's a lot to get through. So this is a busy slide, but I've just updated this map here. So this, if you haven't seen it before, is the way the world fish see it. So this is the Spillhouse map projection. So this is Antarctica here. This is Australia, New Zealand. This is the big Pacific Ocean. You've got Indian Ocean, Atlantic Ocean there, and that's the North Pole there. So that's a landlocked polar region. And you can see some ocean currents on there. So you can see really Antarctica driving the ocean. I really like this perspective because it really shows that we have just one ocean. So all the yellow dots are the ocean drilling program. So you can see there's some really great coverage even around Australia. And the little red dots, if you can see them, that's the ICDP program. So you can see this map projection isn't the best for the continental drilling program, but there is a lot in Europe and more recently in Africa, which actually has a lot of significance to us for definitely the climate stuff. So it's just some quick drilling stats to get your head in the game of what we actually do. So for the ocean drilling program, we've done 500 kilometers of core. That's a lot. For the continents, they've done 120 kilometers. They're both long-term programs, but the IODP program is just a bit longer. We typically drill for the ocean drilling program is about 500 to a kilometer, 500 meters to a kilometer, and the continental drilling program likes to drill 500 to about 5 Ks, but most expeditions are around 500 kilometers of recovery. In Ron's, the director's expedition just last year, they got a Guinness World Record, official Guinness World Record for the deepest ocean drilling core for scientific drilling. And the continental drilling program, I didn't have time to find the exact record, but it's about that. The hottest borehole makes sense that the continental drilling has actually drilled hotter, and that's because they have that huge scientific objective of geothermal. The programs, the ocean drilling program has amounted to about 35,000 papers, scientific papers, and the continental 12,000, so that's huge, huge numbers there. And I won't touch on the scientific highlights too much. I just wanted to touch on the first one because this is more about impacts, this talk. But it has opened up new frontiers to whole new scientific domains, like deep biosphere, paleoceanography, and biostratigraphy, especially my field, radiolarians. So ANZIC members, so we are changing at the end of this year. We hopefully have spent down all our ASC funding, and now we're fully under AuScope, which is absolutely amazing. There are some changes. Macquarie University will be out at the end of this year, unfortunately. Same with Wollongong, but hopefully they will come back in. And hopefully we'll get new members too. The other one is obviously GNS and NIWA have merged. So continental drilling. So the program we've only just joined mid last year for Australia, but Australians have been gate crashing the program for 28 years. So you can see 67 different people have actually engaged with 41 ICDP projects and workshop. This membership was definitely long overdue. We've been getting a lot of benefits from this program for a long time. It is a big change for the office to manage because most of the people had to find loopholes. So a lot of people had, 30% of the participants in the past are not affiliated with ANZIC member institutes. So we have to rethink maybe how we engage, especially with industry, since there's a stronger link there. For the ocean drilling program, Australia has had 35 years of discontinuous membership. We've had a little hiatus in the early 2000s. We have had 231 ANZIC expeditioners in total, 176 Australian expeditioners, and 55 in the last 10 years. So we've actually increased. And I just want to highlight that last point. The program does have actually really good gender parity for its co-chief, for its leadership in the scientific expeditions, but we do not in ANZIC right now. So out of the 21 ANZIC co-chief scientists, we've only had one female, and that's been from New Zealand. So the record's still up there for some Australian female-led proposals to get through the system. So this is the framing question for the rest of the talk. I will come back to this slide after some limitations, but I really want to talk for the rest of the time about how does drilling into the Earth's past help us build a resilience for the future. So quickly, well, not too quickly, is some limitations on impacts. So a big benefit, I think, to the program, and I don't think it's ever going to change, is actually hurts our impact kind of story, is the IP. The program does prioritize open access data and samples to foster that global collaboration. So we don't have that many patents, and I know industry sometimes gets a bit, avoids the programs a bit, but we can do MOUs and find ways around that. Scientific and media systems value, mostly social media systems, value novelty and publications, not synthesis for policy. So there's not much incentives for scientists to actually follow through to the policy pathway. So indirect pathways dilute attribution. So I've got a lot of stories. I'll show you an example of this, that a lot of scientists, you probably don't know where your science actually ends up in the policy space half the time. So we have a lot of stories, especially at this fundamental science level, ending up in policy a long way down the line. There are long publication cycles and delays to output. So at least in the ocean drilling space, it can take up to 20 years to drill. There can be a lot of shorter times too. It can be 2 to 5 years. There's been history of that. But then you have 2 years of moratorium, and then for that full realized potential, at least the publications, we've seen about 10 to 20 years before it starts to plateau after each expedition. The other point is this avalanche of excellence. We serve all these fields of science, all these different scientists, microbiologists, physicists, chemists, the whole shebang. And we also have such a huge output of data. NSF actually described the program as the highest return on investment out of any scientific program. So it's a very big surprise that they've defunded the JR early because of that statement. So ocean drilling averages 9 high-impact papers a month, and actually averages 1.6 papers a day over that 57-year history. So it's a lot, and that's just the IODP. So you can imagine, how do we keep on top of this? There's this paradox, this perilous paradox that happens, especially in the office, of how do we actually advertise without overwhelming the community? And if anything, a lot of the science is buried, much like the course. So there's a slow adoption and translation of results at times. And a big one, I think definitely for maybe this community, they already know about this, especially our Earthbite group, the visibility, discoverability, and usability of scientific data drilling. And the science can be difficult at times. I know the Earthbite group has done a lot of synthesis to try to standardize it, to put it into their G-plates models. And more recently, the Earthbank group hopefully will talk more of trying to create more discoverability through that portal. So sticking with some limitations, I just wanted to highlight some of these. So this is an indirect impact pathway, diluting attribution. So we're going to look at Jodie Webster's expedition from 2010. So this drilled off the Great Barrier Reef, revealing Holocene reef growth and sea level still sands. This data is actually integrated into the Queensland Reef 2050 plan for erosion modelling, and it's actually influenced a lot of that infrastructure, some of the fishery stuff, and some water quality. So it drilled in 2010 here. Oop, wrong way. And next, they got the cores. There's Jodie. This is actually the Hawaiian drown reef expedition, pointing to that initiation, but it was a cool photo I had to add. So 8 years later, after drilling, there's this beautiful paper that did incorporate a lot of other research too, definitely from the investigator, but a huge highlight was that IODP work, just a little bit further offshore on the area. So next we have, there we go. This report actually fed into the GIA models used for understanding sea level changes. Sorry, getting confused by the flipping screens. And this GIA model is actually fed into the Outlook reports for the Great Barrier Reef. And then these reports fed into this long-term sustainability plan with the credit diluted down to drawing on the Great Barrier Reef's Marine Park Authority's ongoing monitoring and research. So we've completely lost that attribution or that visibility of the program's contribution here. But we have many stories like that. This is the long publication cycles and delayed outputs. Again, this is a limitation I just wanted to highlight. So this is publications by expedition going about back to the early 2000s. So this is the 2 IODP programs. And this here is the y-axis, and you can see up to 300 publications to some of the expeditions alone. But you can see this general trend through time. That's about where's the 10-year mark? 10-year is about here. So you can actually still see 10 years later, there's still a trend that these expeditions are still publishing quite high. So let's look at one of these in a little bit closer. Let's look at this big one. This is the South China Sea expeditions. So you can see it's on the same y-axis, so that's 300 publications there, and you can see this is 10 years back in time, so you can see how this publication curve is going, and almost 100 publications just from last year, 10 years later. So you can see that it's not even slowing down yet, it's still going. This other limitation, this avalanche of excellence, we have 35,000 papers tall and still very invisible to most of humanity. These are just the high impact papers. And you can see here on the x-axis, this is 850. So for these 2 journals up here, it makes sense that paleoceanography and paleoclimatology, there's 850 papers there, and for Earth Planet Science letters here too. But we can look down at Nature with a 48 impact factor. That's about 350 papers there. Science itself is around 250 papers too. So again, this just avalanche of how do we actually communicate when we're so overwhelmed. So going back to the framing question, I'm going to go through a few more examples. So just looking at here, some of our impact pathway examples. So both programs support multiple policy priorities. There's examples in risk mitigation. There's a lot of examples in science diplomacy, industry partnerships and resource development. There's examples in defense and sovereignty. There's examples in cross-disciplinary engineering and space exploration. We'll end with a fun one, if we have time. So starting with science diplomacy, I know this is an old example, but I think it's very relevant in today's geopolitical landscape. So the first 2 countries to join the US in 1974 during the Cold War is USSR and the former Republic of Germany. So this was very unique and unusual. It was labeled as a track 2, a model for track 2 diplomacy. Today, as we face climate, ocean health, and resource challenges, DSDP does remind us that science can bridge these divides where policy cannot. So investing in international research, not only for knowledge sake itself, it's a tool for peace, stability, and shared future. Quiet diplomacy in a flashpoint region. This is very relevant today, definitely with the Chinese drilling program just about to get launched and try to not take over, but fill in that hole of the US stepping back a little bit. So in the last 10 years, so that's these red dots here, the last 10 years of drilling, the older dots are ODP, older drill sites. So in the last 10 years, there's been 4 expeditions in the South China Sea, 110 scientists from 16 nations, including China and its neighbors. So you can see there China, Taiwan, Philippines, Vietnam, Japan's there too, we should mention, all sailing together for science. And these expeditions alone were so essential for paleoclimate proxies, for regional agricultural hazard modeling, and global climate modeling. To touch on really quick, to get through everything, just industry partnership and resource development from DSDP's first expedition to understand salt domes. The offshore oil industry was able to explode its work and discovery in gas hydrates, and also how does the ocean store carbon as well on that other side, has been absolutely revolutionary, and the return to industry has been so astronomical that I think even if we asked for it, 0.00011% of royalties, we'd probably be the richest program in the world. So deep sea mining as well, there's a lot of work here, but maybe not what you think. A lot of our deep sea biologists in our community are actually part of this, started this COBRA, which is the Coastal Ocean Biosphere Research Accelerator, and they're the actual main authority to policy that's actually slowed down industry to say, hey, there's actually a lot we don't understand. And they're coming to a conclusion this year, so they've done amazing work to actually help industry understand and to really understand that deep biosphere space. There's estimates that in the water column, if you chuck all the biomass together, there's only 1% of the Earth's biomass in the water column. In the rocks itself, it's estimated at 13% of the Earth's biomass. There's a lot of life down there. Critical minerals, so definitely ICDP program currently is drilling the roots of a rare earth element deposit. So hopefully next year we can have some results and have some talks about that in the discoveries, but we've drilled the Brothers Ark volcano, understanding all those deposits in the ocean and how to discover them better. Nuclear waste disposal. So there's been some expeditions and some work on the kind of mud layers and how they actually retain, and if that could be used as storage, waste disposal offshore. There's currently a little bit of an uptake of offshore hydrology, which I'm really excited about. We got Sarah here in the crowd, somewhere up the back, go talk to her. She just came off an expedition that was solely focused on offshore aquifers and how they impact the system, and there's a whole slew of amazing research coming off that. Next year's distinguished lecturer has been confirmed. It's the chief scientist from this expedition, so hopefully we'll see some proposals definitely coming out of Australia of our offshore aquifers, maybe the Great Barrier Reef, how does La Nina, El Nino affect the offshore ecosystems there, maybe Adelaide and also Perth. So hopefully a lot more in that space too. So the programs support multiple policy priorities. There's a lot of IPCC contributions and lead authors, but I just wanted to highlight one because this is probably our biggest impact as well, is the Antarctica expeditions, or those high latitude expeditions, especially for our region, foster a whole new generation of continental scale ice sheet models. So this really improved sea level predictions in the IPCC scenarios. Just to quickly get through. 2 minutes. We've also helped with agriculture in Australia. So this expedition in the Indian Ocean actually helped understand the Indian monsoon and proxies for hydroclimate forcing. Again, IPCC cites it, but it's also in the WA Department of Agriculture policies. Defense and sovereignty, just a quick example of Japan here. So the EEZs here, and sort of these 3 areas have actually been, or 4 areas here have actually been confirmed. So they've extended their continental shelf, so they don't have rights to the water column, but they have rights to the seabed. So this is very significant for Japan. So they've extended it quite significantly, as you can see. For Australia and New Zealand, there was a big grab, a huge effort from GA and GNS. But it did incorporate a lot of ODP cores, so to say. So we've extended our continental shelf, so that's all that kind of little purple area, so the size of Western Australia for us, and for New Zealand, about the size of the actual continent. We don't need this for offshore mining right now. We have enough minerals definitely on Australia, but this has safeguarded our future. So the geophysics really helped map that, and the IODP cores really confirmed that that's continental crust. Very easy science. So wind farms is also a big one. This was meant to be America's largest offshore wind farm. Just 2 weeks ago, Trump has stripped $112 billion off the offshore wind farm industry, but they're still going ahead because there is a crisis, especially in New York City. So this is New Jersey here. This is the IODP core, or the old ODP cores. There was a lot of geotechnical studies as well done, but they had to come back to the IODP cores because they just provided the better borehole data needed to actually build this infrastructure. So this site has been put on hold. This site here is actually under development right now. That's the Empire wind farm. So there's 54 wind farms going on there right now. And that's to supply Brooklyn. Risk mitigation, I'm not going to talk too much because we don't have this much in Australia, but the borehole observatories for earthquake monitoring is absolutely astronomical. We just had our distinguished lecturer go around, talk about this offshore Hikurangi, but the New Zealand one, they have the offshore, the little triangles, if you can see them, are actually feeding live information into the Japanese warning system. Space exploration, going to the really exciting stuff. I'm almost done, I promise. So some translation of actual infrastructure. So from the JR to space, thanks to NASA, the deep UV bioinspection tool, DEBBT, was developed to find subsurface microbes on the JR. It's now on Mars. It's called the Sherlock system because it had to get downsized. And it's on the Mars Perseverance rover. So that's the IODP's DEBBT tool, and there's the little stabilizers, there's the drill, so it's downsized nicely. I will skip that one, and I will end on sort of this example, because it's always fun. We don't have that much manufacturing in Australia, so I thought this was nice to highlight that we're actually quite known in the scientific drilling space, that our Aussie roller drilling cone bits are actually was used on the JR since 2017. And yeah, just to end here is just again our 4 strategic pillars in ANZIC: to nurture partnerships, facilitate access to infrastructure, foster the skills pipeline, demonstrate outcomes and impacts. Looking ahead, we really hope, you would have noticed there was a lot of ocean examples, really hope that under ICDP membership we can get a lot more in integration there. I'm looking forward to that. Strengthening regional leadership across the Indo-Pacific, so a lot more engagement in the Pacific region. Expanding inclusion and career pathways for emerging scientists. Okay, I'll end there.
How good. Thank you, Sarah. I don't think we've got time for questions, so we will carry on, but Sarah, you'll be around to chat with people during morning tea, during lunch? Oh, okay, great. Is there a question?
It was
Going
a lot.
Once, going twice.
It's that avalanche of excellence.
Maybe you're off the hook. Oh, yep, over here.
Hey, thanks for such an informative presentation. I'm just curious, like with so many publications coming out, what would you just personally, like what are some ways where you would like to have all that information more easily disseminated?
Yeah, again, with the change of program, so the mothership, which was Texas A&M, they had a team of 12 people just working on the publications alone. So that is getting downsized. So they kept on top of it really well, and they sort of fed it to us. On the ANZIC side, we really tried to highlight the ANZIC stories pretty much, or if there is a story offshore that we think is of national significance, like the offshore aquifers or the rare earth element deposits in Malawi. So we be selective. So again, a lot of it stays buried, unfortunately. And maybe that's the slow adoption, but I don't have a solution. Does anyone have a solution? I would love to hear. It's a huge issue, and yeah.
Thank you so much, Sarah. Awesome. We'll move to the next speaker, and I'm very glad with the AuScope rebrand that it does include Tasmania, because we have Tiege McCarthy, who is the postdoctoral research fellow with the AuScope VLBI project at the University of Tasmania. Let's give a round of applause.
Okay, thank you very much for that. I'm just going to set up my timer. And this clicker. Okay, yeah, so my name's Tiege. I'm from the VLBI group at UTAS. And this talk is going to be a brief overview of our AuScope VLBI array, which has now been going on for about 15 years. So yeah, forgive me, but we're going to be moving from looking downwards to now looking upwards. So I'm going to start with a short introduction to VLBI, or Very Long Baseline Interferometry, and why it's important. So essentially, we're using arrays of radio telescopes to observe extremely distant radio-loud black holes, which are also known as quasars. These sources are so extremely distant that we can essentially treat them as unmoving reference points in the sky. And when we correlate the data from simultaneously observing these black holes with multiple radio telescopes, we can determine delays in the wavefront arrival at the different telescopes, and this is our primary observable in VLBI. So, a typical VLBI experiment runs for around 24 hours, and we observe hundreds of radio sources, and we generate thousands of different delays between our pairs of telescopes. These delays allow us to determine the positions of the radio telescopes during the experiment, throughout the experiment, as it changes with time. We can then compare these positions to those that are modelled through understanding of the current Earth orientation parameters and the delays that we expect with the rotation of the Earth. And then we can do some least squares analysis and actually define updated Earth orientation parameters. And the thing that makes VLBI unique, so there's 4 different pillars of space geodesy. VLBI is the only one that can measure all 5 Earth orientation parameters directly, so we can measure the Earth rotation, which is also known as DUT1. So why is this important? Why is VLBI important? Everyone here would know how important position navigation and timing systems are to modern society. They underpin lots of critical technologies such as transport, agriculture, financial systems, science, and defense. However, these satellite systems are only as good as the reference frames that they rely on, and this is where VLBI steps in. And over the past 40 years, these reference frames have been maintained as a research endeavour. However, they're so important that this is really something that's needing to change, and organisations such as the UN have identified that this is an area of risk. So speaking of the UN, the Global Geodetic Centre of Excellence, the UN's Global Geodetic Centre of Excellence, has identified that the global geodesy supply chain is perilously close to critical failure. In response, UTAS has now become an official partner of the UN GGCE, and together with the support of Geoscience Australia, we're trying to fortify at least the VLBI part of this global supply chain. So currently we're providing, we have the AuScope VLBI array, which is the radio telescope section. We have the analysis centre at Geoscience Australia, which is an official IVS analysis centre, and I'll get into what that is in a minute. And then also the sort of interim step, which is correlating all of the data from the telescopes and putting it into a form that the analysis centres can use. We're currently working on a UTAS Geoscience Australia joint venture to shore up this area as well. So, getting into the AuScope VLBI array, it was originally funded by AuScope and is now operated by the University of Tasmania through a partnership with Geoscience Australia. It consists of 3 12-metre radio telescopes that span the continent of Australia. So we have one in Hobart, Tasmania, we have one in Yarragadee, WA, and we have one in Katherine, Northern Territory. This array was originally built as an intermediate between the old legacy VLBI network and the new VGOS, or the VLBI Global Observing System network, which I'll get into in a second. With the first, Hobart 12 was originally commissioned, or saw first light at least in 2009, and the full array was up and running and participating in international geodetic observing by 2011. So just talking about some of the upgrades we've made to the array on the way. As I mentioned, it was originally commissioned as an intermediate, so it didn't make sense to put on the next generation of observing equipment on these antennas. because there was no other VGOS antennas for us to observe with internationally. So we commissioned it with the old legacy system, and then through an ARC LEAF grant, or ARC LEAF grant, we upgraded the receivers from 2018 to 2023. And this allows compatibility with the new VGOS network, as well as through some clever additions to our signal chain, we also maintain compatibility with the old legacy network. So why are we moving from legacy to VGOS? Essentially, I guess the short story is a fully realized VGOS system increases the precision by an order of magnitude. So we move from centimeter precision in our baseline repeatabilities to millimeter precision. And it achieves this through a number of different factors. So we have a larger frequency coverage, we use wider bands, we use higher data rates, and we have faster moving telescopes. And you can see in the top image here, this is at Koki Park in Hawaii, so it's a US-run facility. On the left-hand side is the original legacy telescope, and on the right is the replacement VGOS telescope. So they're much smaller, but they're much faster and more sensitive. One thing to note is that because our array is sort of an upgraded array from its intermediate point, we don't quite meet the full VGOS specs, so we're a bit slower. We're still faster than older legacy telescopes, but we're about half the speed of modern VGOS telescopes, and we have about half the sensitivity. But we're also some of the only telescopes in the Southern Hemisphere, so still make valuable contributions. And the plot in the bottom right is essentially showing where we're at with precision of VGOS. So currently, we're about a factor of 2 to 3 more sensitive than the legacy network, but we hope with future and further refinement we can achieve that factor of 10 or the order of magnitude. So another new exciting upgrade for the AuScope VLBI array has been upgrades to our network connectivity. So moving from legacy to VGOS means that each of our telescopes in a 24-hour session produce about 40 terabytes of data per day. And this is up from around 3 terabytes with the old system. And so until a year ago, Hobart was the only one that had a fiber connection. And so we were physically shipping the data from the other 2 remote stations to Hobart, and then either processing it there or onwards transferring it over our fiber link to the US or to Europe. But this has now changed thanks to some funding from AuScope. We now have 10 gigabit links at all of our remote stations. And so we can do away with physical shipping, and we can lower our latency, and this also enables new and unique observing programs. So before I get into our contributions, I'm going to quickly go over what the IVS is. So the IVS essentially organizes all international VLBI experiments. It's a global collaboration between 20 plus countries, and it operates on a best effort basis. And so they have input into coordinating or scheduling experiments, how the stations are running, how the correlation centers are running, how the data centers are running, and how the analysis centers are running. And they organize around 200 or more than 200 24-hour sessions per year, and over 1,000 intensive 1-hour sessions per year. So this is our contribution. And in the top right, we have a animation from a colleague of mine, which shows for 2025 all of the experiments that have been organized for the IVS. Anytime you see blue lines, that is where Australian VLBI stations are participating and have baselines to other stations. So you can see that we're involved a lot. And over the 15-year lifetime, Hobart and Catherine have both been in over 1,600 VLBI experiments, with Yarragadee over 2,000. And we are the busiest stations in the IVS, so I think this plot in the bottom right is only limited to the top 15 stations, but there's more than 15, and we take all the 3 podium spots for busiest stations. This is for 2025. And the reason why we are so busy is because we have the backwards compatibility with both networks. So we can participate in legacy observing, which is still far more common, and the newer VGOS sessions. In addition to our contributions to the IVS, we also run regional sessions with partners in South Africa, New Zealand, Japan, and we also run a Southern Hemisphere experiment to monitor Earth rotation. I'm going to go through this really quickly. This is just the over time contributions, and where the red lines are, you can see that's where we did receiver upgrades. And we had long gaps from the receiver upgrade to getting back into full swing observing because we had to prove our backwards compatibility to the IVS before they let us participate again. So something that comes from our new upgrades is the ability to independently measure the rotation of the Earth. So this is super important to measure because it changes daily on timescales of days. It is best measured with long east-west baselines, which necessitates international collaboration, and it is critical to satellite navigation and defense applications. But we've done a recent simulation study that shows that our upgraded VGOS receivers mean that we can actually measure this quite well with just our AuScope array, our 3 stations. And having this increased network connectivity means that we can achieve this at low latency, which is required for these frequently changing values. I'm going to have to pick up the pace a little bit, sorry. Another new use for the array is through what we're calling space ties. So traditionally, the GNSS geodetic system and the VLBI geodetic system are tied together through local surveying. So physically from the VLBI station to the GNSS station. But the ability to observe GNSS satellites directly with VLBI allows us to position them with reference to the black holes which define the reference frame. Historically, this hasn't been possible because the GNSS signals aren't observable with radio telescopes. However, we've developed a new technique that allows this to happen, and further refinement of this technique will allow us to play a critical role in future space missions, such as the Genesis ESA mission launching in 2028. And I'll touch on a couple of the current challenges that exist at the VLBI, well, for VLBI in general and also at our array. And one of the big challenges is radio frequency protection. So geodetic VLBI is categorized as a radio astronomy service, but our VGOS bands fall outside of this RAS allocation, so we're broadly unprotected from radio interference. As communications technology, both terrestrial and satellite, advance, we are quickly those technologies are quickly covering the radio spectrum, and this really has significant impacts on our results. And I've noted there that space-based comms are particularly destructive to geodetic VLBI because essentially they're sometimes broadcasting signals right down the barrel of our telescopes. So an important challenge is we need to advocate and increase the awareness of VLBI. And there's an article in the conversation that my colleague Lucia wrote, which is a great starting point to get some information about this. A few other challenges we have is that we're a research facility that's operating like a national facility, and we currently have a FTE to telescope ratio of approximately 1:1, which is crazy. And we have a few single points of failure which just come from being a research facility, but we're planning on actioning contingency plans for those in the near future. And then quickly, what else are we up to? I mentioned before the Correlation Center, and we have a lot of astronomy happening on the array also. So a colleague of mine is doing some methanol maser astrometry using the array. His project's called Spirals, and they do maser parallax distances to spiral arm masers, so you can help map out the spiral arms of the Milky Way. And then we had a PhD student who was recently using the array for space weather, looking at solar, wind, and coronal mass ejections. And that's it. Thank you.
How good. Thank you so much, Tiege. I think we might skip the questions in the interest of time and welcome our next speaker. So we have Matt Garthwaite, who is an Earth observation scientist at CSIRO's Center for Earth Observation. I'll give you the mic and I'll get you all set up. Thank you.
A round of applause. Good morning, everyone. This morning I want to talk to you about what I believe is a fantastic opportunity to establish new ground motion data infrastructure for Australia. I would also like to acknowledge Matt King for establishing some of the narrative for my talk today. I stole some of that narrative from a keynote presentation he gave at the Locate conference earlier in the year. So just to raise your awareness and building on the previous talk by Tiege, AuScope has invested now for nearly 20 years in infrastructure for geodesy and geodynamics research. As Tiege pointed out, there's been a big investment in very long baseline interferometry, but it also covers investments in satellite laser ranging, global navigation satellite systems, gravity, and much more. And a lot of this infrastructure has been implemented by colleagues from Geoscience Australia in the audience. And of course, this research infrastructure has enabled some fantastic geospatial research. I'm going to use one example to highlight that, picking up on the expansion of the global navigation satellite systems network in Australia. So AuScope expanded the scale of that national network from around 20 sites to over 100 sites back in 2018, implemented by GA. And this enabled a team from the University of Tasmania to do a really in-depth analysis of the subsidence or vertical land motion of the Australian continent. And what they found is that across that 100-site network, there's a pretty consistent observation of subsidence in the range of 1 to 2 millimeters per year. That's quite interesting because models of glacial isostatic adjustment do not show that same subsidence effect for Australia. We're very far away from where glaciers were dominant in the last ice age. So we don't really understand why we're observing this subsidence in Australia. And this subsidence has a big implication for measurements of sea level rise. Sea level rise is typically measured on tide gauges, which are installed on the land. The map here is showing with the squares the locations of our national tide gauge network. There's around 20 sites there, distributed around the coast. And those tide gauges measure relative sea level rise compared to the land which they're founded on. Meanwhile, absolute sea level rise can be measured through satellite altimetry. That's been done for more than 2 decades now. And if you subtract the absolute sea level rise measurements from if you subtract the relative sea level rise measurements from tide gauges from the absolute measurements from radar altimetry, you can again see that Australia is subsiding, and that's what the colors of the square symbols are showing. Not only that, it's not a consistent view across the whole of the continent. There is variability in that sea level rise. So we need to understand whether that is a real phenomenon. And then in the last decade, another geodetic technique called satellite INSAR has gained prevalence in being able to map in more depth the local patterns of ground motion for various areas. I'm showing an example here from City of Brisbane. And what you can see here is that the color's prevalently blue, so there's generally a subsidence occurring here in Brisbane. But there are localized patterns of movement being picked up in these satellite measurements on the order of 2 millimeters per year. One of the areas where there is a particularly high amount of movement is in the port of Brisbane. And if we look closely at that area, we can see, particularly at the north of the port of Brisbane, there's very large velocities of ground motion, up to about 40 millimeters per year. This is actually due to a recent expansion of this port over the last few years. So they've reclaimed land from Moreton Bay, and there's subsidence occurring in the sediments as they compact within the seabed. So this has big implications for the long-term sustainability of the port, given the effects of sea level rise. So INSAR, I think, has a role to play in being able to pick up where these phenomena are occurring, and if you look back on the big map, you can see that the tide gauge in Brisbane is shown by that purple triangle. That's actually very close to the Port of Brisbane, but there's a gradient of ground motion between those two locations. So the good news is that there is an INSAR data revolution underway globally. There was fantastic news, two pieces of fantastic news this year. The NASA Indian NISAR mission was launched back in July. This is an innovative L-band radar mission, which has a rather fantastic umbrella-looking structure, which managed to unfurl in space without issue, so that was great news. And then the European Sentinel-1 constellation has now been in service for over 10 years. The first satellite, 1A, was launched in 2014, so it's already collected 11 years of data. And then December last year, the third satellite, 1C, was launched, and then just a few weeks ago in November this year, 1D was launched. So this is great news for INSAR, and showing the data coverage that the globe receives from Sentinel-1. In this map, you can see that the vast majority of the global landmass is covered, including Australia, from this mission. And the really important thing about these two systems, NISAR and Sentinel-1, is that the data is open and free. So in Australia, we can access this data for free. And this has led a lot of innovation around the world in recent years in developing ground motion services that leverage the free satellite data and make publicly available the insights like I showed on the previous slides. So examples of those are the European Ground Motion Service, the North American Displacement Portal developed by NASA, and even a ground motion product in New Zealand. I'm afraid to say Australia is lagging behind in leveraging these open data sets. So just to quickly show you some of the existing examples, this is the European Ground Motion Service. It's an open web portal. There's a website address. You could go and have a look. You can scroll around Europe and zoom in and find subsidence effects. This is an example of the Groningen gas field, which is well known to be a subsiding area. And you can see a displacement time series graph that you can extract from that European Ground Motion Service for free. And then the Americans released this year their North American equivalent product. This has been an effort through NASA JPL and released by the Alaska Satellite Facility. You can see in the example I've picked out, this is the Vancouver International Airport. In quite a small area, you're seeing areas that are stable, and then right next to it, areas where there are ground motion occurring next to active runways. And then this is the example from New Zealand. So in New Zealand, there's a public-private partnership between the former GNS Science, now Earth Science New Zealand, and a British company to produce a national-scale INSAR-based ground motion product there. So the obvious question is this possible in Australia? Well, as I pointed out before, the data does exist and it is free. So we can access that. The challenging part is it is very large data sets, and we need to be able to translate those raw satellite images into the ground motion insights. That's where compute is important, of course, and in Australia we have fantastic compute facilities, both National Compute Infrastructure here in Canberra, the Pawsey supercomputer in Western Australia, and other cloud-based systems like the CSIRO EASY platform, which has been developed to leverage open data cube technology and work in the Amazon Web Services environment. So, tick and tick. What about whether INSAR has been proven in Australia? Well, yes, it has. There's been quite a lot of localized projects in Australia through government, academia, and industry over the years, which have found that INSAR does work, and I can show you an example of that here. This is a local example from a landfill site here in Canberra, just down the road. Geoscience Australia had established a GNSS monitoring network at this landfill back in 2020, and we used that as an opportunity to compare the positioning data from GNSS against what we get from Sentinel-1 INSAR. The middle panel there is showing you the INSAR results over the landfill for 4 years. There's about 40 centimeters of ground motion being identified there. And on the right-hand panel, I'm showing you the comparison of one of the GNSS sites versus the INSAR. And you can see what I would say is a pretty good match-up between those two techniques. The RMSE is on the order of 7 millimeters, so sub-centimeter comparison, and the residuals are even less. They're about 4 millimeters. So through validation exercises like these, we can prove that the remotely sensed-based technique of INSAR can be believed, and then scale up these sort of analysis for larger areas. So this is my final slide. Is this possible in Australia? Yes, it is, but we do have a bit of a skills gap and workforce shortage around INSAR technology in Australia. We have experts, but they're few and far between and not working in a coordinated fashion. So to try and remedy this, AuScope has recently led the submission of a proposal to NCRIS to establish new digital research infrastructure, which we're calling the Australian Ground Motion Infrastructure. What AGME will do is generate these large-scale ground motion data sets using INSAR and leveraging the free and open data sets from Europe and America, Sentinel-1 and NISAR. It would distribute these data openly so that there's a foundational data layer for research to be done, particularly on important problems like sea level rise and coastal hazards. Importantly, it would build a sovereign expert NRI workforce, so raise the capacity and capability within our science people in Australia to develop these data sets, but also make use of them. And also to drive adoption of these technologies in Australia, meaning that across government, academia, and also industry, I think there is really an opportunity to stimulate commercial opportunities off the back of an infrastructure like AGME, so that essentially we can monitor more ground motion issues across a range of phenomena. So I'll leave that there today, but would like to thank collaborators across CSIRO, Geoscience Australia, University of Tasmania, and Curtin University for working together on this proposal, and we hope we're successful with NCRIS. Thank you.
How good. We have time for a question or two, if anybody has anything that they'd like to ask. You're all like, morning tea is next and we want coffee. Is that what's happening here? Well, thank you so much for that, Matt. A couple of housekeeping things before we go to break. One is we have less access to the building than what we did yesterday. There's a room called the Becker Room, where there are a couple of bags and a laptop, and Joe kindly moved those across to another room called the Dorothy Room. So in case you're like, where's my bag? It's in the Dorothy Room. And if you're not sure which rooms we have access to, just ask one of the AuScope team. And we do have access to the Dorothy Room only until 3 p.m. So just letting you guys know, we've got a little bit less access to the venue. Did I say all of that correctly? There is more. The other thing I'll mention, if you want to come up and tell us about them more, is for all the speakers in the second half of today, if you don't mind sticking around before we go to morning tea, some information that we'd like to share with you, and I'm going to pass over to Joe.
Hello. The more is just that after 3 p.m, the bags have to move out of that room they're now in and can come into either here somewhere or into the foyer. And they should be pretty safe in the foyer because the front doors and every door around the complex is locked. Makes sense? Cool.
Let's all go for morning tea. We'll be back here in 30 minutes. Thanks, guys. Let's give each other a round of applause.